With some probability, even a simplified tree diagram is quite complicated. For example, here we have a bag containing 6 red and 4 blue marbles. We're going to select 4 marbles without replacement. If I drew a tree diagram, the first marble red or blue, the second marble red or blue, and so on. And then I still have to work out all the probabilities. So to start with, we've got 6 out of 10 red and 4 out of 10 blue. But after we've drawn a red marble, because it's without replacement, I've now got 5 out of 9 and 4 out of 9. And then after we've drawn a blue marble, we still have 5 reds, 5 out of 9 and 3 out of 9. You can see that it's going to take a while to work out all of these probabilities, and I don't even need most of them to work out the problems that I've got here. So what we do instead is to imagine a tree diagram. What's the probability of selecting 4 reds? Well, I imagine the first branch would be 6 out of 10, and then if I keep selecting reds, I'm following the 4 red branches one after the other. And so once I've selected a red marble, I've now got 5 out of 9 red, then 4 out of 8, then 3 out of 7. Using the same strategy, the probability of selecting 3 blues followed by a red, I'm going to imagine tracing along the 3 blue branches followed by the red. To start with, I've got 4 out of 10 blues, and because it's without replacement, the number of marbles in the bag is going to go down by 1 each time. And I'm selecting 3 blues in a row, so that number is going to decrease by 1 each time. But then the last one is a red, and there are still 6 reds in the bag. Similarly, the probability of selecting 3 reds in a row followed by a blue is 6 out of 10 multiplied by 5 out of 9, 4 out of 8, and then we've still got the 4 blues in the bag. But what if the question was, if I draw 4 marbles at random, what's the probability only one of them is blue? Not necessarily the last one is blue, it could be the first one that's blue or one of the middle 2 that's blue. The probability that the first marble is blue, we have 4 out of 10 marbles with a blue, and then the rest are red. So then we've got 6 out of 9, 5 out of 8, 4 out of 7. Same answer. And it's the same if the blue is the second marble, or if the blue is the third marble. Because you can see the denominators are identical, but we're just changing around the order of the numerators. So my final answer, what's the probability that from the 4 marbles I'm going to have 1 blue and 3 red? An alternative method would be to use counting techniques. If we think about it, we're choosing 4 marbles from the original 10, and from the 6 reds we want 3 of them, and from the 4 blues we want 1 of them. So check with your calculator that this does give the same result as when we think about an imaginary tree diagram. In this example, we've got 2 bags of marbles, bag A and bag B, and they contain 5 marbles each, but different numbers of reds and blue marbles as shown. I'm going to roll a normal die once. If it's a 6, we're going to select a marble from bag A, and if it's not a 6, we're going to select from bag B. So you can imagine you could set up a tree diagram where you've got 6 and not 6, followed by bag A and bag B. But we're going to imagine the tree diagram. So the probability of choosing a red marble, well, firstly we need to know whether we're going to roll a 6 or not. So if we take the option that we roll a 6, so that's a 1 in 6 chance of rolling a 6, and then we would multiply along the branches, and we would look at the probability of selecting a red marble from bag A. Plus the other option would be that we didn't roll a 6, so So that has a probability of 5 out of 6, and we would multiply the bag B probability of selecting a red, which is 1 in 5, resulting in a probability of 7 out of 30 that we select a red marble. I'm going to summarise some rules of probability here, but I say use with caution because, as with any area of mathematics, it's not a good idea just to blindly follow rules without understanding the context. And even though it takes a little bit longer, it's usually a good idea to write out the sample space using a Venn diagram or a tree diagram to get more of an idea of the situation rather than just applying rules and hoping the answer will drop out. So complementary events are usually described as event A and A dash, or not A. And the probabilities of complementary events sum to 1. So if we want to know the probability of not A, it's 1 minus the probability of A occurring. With conditional probability, we're looking at the probability of an event occurring given that another event has occurred. So this is the probability that B occurs given that A has occurred. So our denominator is the probability of A occurring. But because we're given that A occurs, the numerator is the probability of A and B both occurring, the intersect of A and B. So when we talk about A and B occurring, that's what we mean, A intersect B. And if we want the probability of them both occurring, we can rearrange this conditional probability formula to get the probability of A and B occurring is the probability that A occurs multiplied by the probability that B occurs given that A has occurred. This is like multiplying along the branches of a tree diagram. However, if the events A and B are independent, it means that the probability of B occurring given that A has occurred is equal to the probability of B occurring. So only for independent events we can replace this formula with probability of A and B occurring is the probability of A multiplied by the probability of B. A or B is represented by A union B, and the probability of A or B occurring is the probability that A occurs plus the probability that B occurs, subtract the probability that they both occur. And the reason for that is, if you imagine a Venn diagram, if we add the probability of event A occurring plus the probability of event B occurring, this middle bit, the intersect, has been counted twice, and so we need to subtract it once. However, if A and B are mutually exclusive, the probability of A intersect B is 0. There is nothing in this middle bit, the overlap. And so we can rearrange that formula. The probability of A union B is equal to the probability of A plus the probability of B, because the intersect of A and B is 0. Only if A and B are mutually exclusive can we say that the probability of the union of A and B is equal to the probability of A plus the probability of B. I'm going to work through some examples which use these rules of probability, and as always you should pause the video and try them for yourselves before you watch my solution. So here we've got the probability that a person is diseased is 0.001, and if they are diseased, the probability they will die from the disease is 0.7. So we could say that this is the probability of A. So event A is that a person selected at random is diseased, and this is the probability of B given A. So this is saying event B is that somebody will die from the disease. So really we're looking for the probability that they have the disease and they die from it, which is probability of A multiplied by probability of B given A, which is 0.0007. Here's an example where a tree diagram, or at least an imaginary tree diagram, may come in handy. We have 50 items, 5 of which are defective. We're selecting 2 without replacement. What's the probability that they're both defective? So if we select the first item, probability that the first one is defective is 5 out of 50. And once we've selected a defective item, the second one being defective is 4 out of the remaining 49. So if we say that event A is the first item is defective and event B is the second item is defective, we want the probability of A and B both being defective. So it's the probability of the first one being defective multiplied by the probability the second one is defective given that the first one is defective, which is this 4 out of 49, just 20 out of 2,450. Now we could have solved this using counting techniques. From the 50 items, how many ways can we choose 2 of them? That's the total number of pairs that you can possibly choose from the 50 items. But of those, we want 2 of the 5 defective items and none from the 45 items which are not defective. So check this on your calculator, make sure that it results in the same probability as before. Here we're given some information which is actually conditional probability, and it's probably easier to understand with a tree diagram. So event A is the probability that A fails, and that's 0.05. which means the probability that A does not fail is 0.95. Then we're told that if A does not fail, then the probability that B fails is 0.01, which means the probability that B does not fail is 0.99. And we're also told that if A fails, the probability that B fails is 0.1, which means the probability that B does not fail is 0.9. So the probability that A fails and B does not fail is the probability of A multiplied by the probability of not B given A, which is 0.05 multiplied by 0.9. And the probability that A does not fail and B does not fail is the probability of not A multiplied by probability of not B given not A, 0.95 multiplied by 0.99. Try this example without using a tree diagram, but just using the rules of probability from earlier. Probability of A union B, remember, is the probability of A plus the probability of B, subtract the probability of A intersect B. So in this case it's 0.65 plus 0.6, subtract 0.4, 0.85. This line here means we're looking for the complement of A union B. So this is 1 minus the probability of A union B. So 1 minus 0.85, which is 0.15. And thirdly, the probability of A given B. Remember, the denominator is the probability of B, and the numerator is the probability of A intersect B. So this is 0.4 over 0.6, which is 2/3, or if we want to write it as a decimal, 0.6 recurring.